As you look at the graphs, when we go to write the equations of the piecewise functions, how many pieces do you expect to be present in the equations for each of these three graphs? 2, okay? And those should be linear equations because the pieces that we're looking at are behaving like lines, okay? So for this first graph, go ahead and write f of x equals, give myself a bracket because I know I'm going to need 2 pieces to describe it. And let's start with the branch that's in the domain where x is less than 0. Okay, so I'm talking about the left side of the x-axis. So what would be the equation for that portion? So when you look at this portion of this line, okay, over here on the left side, what do you see as the slope? So to move from point to point, yep, -1, because each time we go down 1 over 1, down 1 over 1. Okay, see? Down 1 over 1, okay, to move from point to point. So -1 is the slope. What is the y-intercept of that segment? 0. Good. So I don't have to write +0. So the equation of that first branch that's to the left of the y-axis, okay, is going to be y equals -x. That's going to be its equation. So then after that, I need to list the domain on the graph for which that branch exists. So what would be my domain restriction on this branch? Yes? Sure. X is less than or equal to 0. And you guys, when you're writing them yourselves, we discussed this last time when we made our function that described our piecewise graph that we made with the CBR. Remember that you guys couldn't see? Okay. We kind of decided which endpoints were filled in and which ones were open because they connected to each other. So it was kind of our call where we wanted to say when it was closing. Okay. All right. What would be the equation of the second branch that we see up here, the one that is to the right of the y-axis? Good, it would just be x, because it has a +1 slope and a y-intercept of 0. And what would be the domain restrictions on that portion of the graph? Or? Good, x is greater than 0. Any questions on the function that we wrote for that first graph up there? All right, so let's talk about part B. Again, we said we see 2 pieces. So again, let's start on the left. I got this picture from something. It doesn't have arrows on it, but see how they go all the way to the end of the screen? It's like a snapshot from a screen of like a calculator or a computer or something like that. So we're going to go ahead and assume that the lines go on forever even without the arrows because it's the edge of the screen. Is everybody okay with that assumption? So if you have it, go ahead and add arrows on it. So if you look back at your notes, maybe you don't know why it stopped or something like that. All right, so first branch to the left of the y-axis, what is the slope of that line? And I'll tell you guys that it looks like it's going through -3 on the x-axis and +3 on the y-axis. So what would be the slope of that line? So 2 over 3. So if it starts at -3, 0, but it ends up hitting there up there at 3. See how the y-axis have it every 2 marked? Okay. So it's actually rising a little bit more than 2 because it has to reach between 2 and 4, which means it's actually rising how much? 3. And then it's going over from -3 all the way to the y-axis, which is over 3 as well. So if the rise is 3 and the run is 3, then our slope is going to be 1. Okay, so our slope is 1. Does that line have a positive or a negative slope? Positive. Okay, remember, we really got to look at it from left to right. That line is climbing upwards. So it has a positive slope. So my m, or my slope, is 1 times x plus whatever my y-intercept is. And what's the y-intercept of that first branch? 3. Good. All right, who can give me the restrictions for that branch of the graph? Good. So x could be less than or equal to 0. Okay. Better mark these since I'm getting a little bit too big. All right, second line. Can somebody give me an equation for that function? Yes. Good. So same thing, same y-intercept, but with a slope in the opposite direction. And what would our domain restrictions be? Good. All right, and then let's look at the last one, part C. So this point down here where it turns around looks to be 1, -4. And then it looks like it crosses the positive x-axis at +3. And then the negative side of the x-axis at -1 if you're trying to see rises and runs. Who thinks that they can give me the entire first piece of this function? So equation as well as domain restrictions. Yeah, Ben? All right, so if you go to -2, okay, does that first branch, we're talking kind of on the left side of the V, cross the y-axis at -2? Yes. Does it seem to go down 2 over 1 to get to another point on the line? Yes. Okay, and does the branch exist from 1 to all the area where x is less than 1? Yes. Okay, good job. All right, who can give me the equation for the second piece or second branch of this graph? Yes. Okay, so I see the 2, and then if I was a little concerned about the -6, if you did extend this line, you could see you're already down at -4. It would go 2 over 1, so the y-intercept would be -6. Okay, but that line only exists when x is greater than 1. All right, I picked these piecewise functions for today, not just to review piecewise functions, but to introduce the next topic that we're studying. What do you notice about all of the functions that we just wrote up here in the branches of their equations? Okay, good. So if you've had any experience, absolute value graphs create a V. Okay? How we could tell that these were absolute value graphs? When you look at each function and you look at the two pieces that we use to write the equation, what's the only differences occurring in the two pieces? Yes. Good. Their slopes are opposite. And then here they have a different y-intercept. That's because we shifted the graph to the left or to the right off of the y-axis, right? So then things got a little more wacky. So maybe it's easier to see with part A and part B. But basically, the big difference is that the graph is traveling at the same steepness. We can change its location, but one side of it has to be a positive slope and one side has to be a negative. Absolute value is what creates these graphs because it's the only thing we have that just measures distance from 0 and doesn't care if you're at -3 or +3. It's going to say the absolute value of -3 is 3, and the absolute value of +3 is still 3 because that's how far you are from 0. Okay, so that's why the slope doesn't matter, which means in these three cases, you actually don't need to write a piecewise function for this. There is one equation that describes these graphs, but you have to use absolute value bars in that equation. Okay, so that's what we're going to be working on today. So first expectation we have today is that we're going to graph things that have absolute value bars in their equations, and that our graph should end up looking like V's. Okay? So we're actually going to do a little investigation. If you have the note guide, it's the next page of your note guide. Okay? If you don't have the note guide, you're just going to have to kind of write down the conclusions that we draw from someone else because they'll be important for you. I'm going to bring it up for you guys. All right, so we already discussed that they're going to create V's, okay? Things with absolute values create V's. And then we're going to use the calculator to quickly get us a bunch of V's, not because we don't want to be able to graph them by hand. We need to be able to graph them by hand. Is that clear to everybody? We'll use the calculator a lot at the beginning to put in a bunch of graphs and quickly be able to show us what's happening when we change certain numbers in certain places of the equation. What do they do to the graph? Because what we're going to see in our course is that over time, it doesn't matter whether you're graphing a quadratic, an absolute value function, a cubic, a square root, a cube root. There are certain forms of the equation that if you write them a certain way and certain numbers exist in certain places, they're going to take the original shape of the graph and they're just going to squish it or stretch it or move it or something like that. And we really want to try to establish what is going to do what so we can quickly graph things by hand in here. Does that make sense to everybody? Okay, so the calculator is the tool we're going to use to make some observations about what happens. So basically, this chart is set up like so. There's a bunch of different equations for you to graph. Notice it asks you for A, H, and K to sketch a quick picture to find the vertex and state whether it opens up or down. So first of all, for the A, H, and K thing, those of you that don't have the note guide, write this down. The general form of the absolute value function. Those of you that do have the note guide, it's up in that paragraph at the top. This is the format of the equation we're looking at. If you're looking at an absolute value equation that's in this form, meaning there could be a number multiplying outside the absolute value bars, there could be a number that's being subtracted from x, and there could be a number added on at the end of the equation. We want to know what these values do. Okay? So notice here it says A is 1, H is 0, and K is 0. That's because the equation graphed here was just this. Next to this equation, and if you don't have the note guide, write down the first one, y equals absolute value of x. If you do have the note guide next to it, write parent function. Okay? How many of you guys have heard of a parent function before? Okay, a couple of us. So the parent function is like the most basic form of that equation. So this is absolute value equation, but it's like the most basic form. There's no numbers multiplying it, nothing being added or subtracted. It's the simplest absolute value equation you can write. The reason those are important is because they give you the basic shape and behavior of the function. Then all the other stuff, all the numbers you add in, it just does stuff to that already existing shape. Okay? So if we graph this on our calculators, we would see a V like this. Anybody know why A was determined to be 1 in this equation if we're looking at this general format? Yes. Good. If there's not a number here multiplying outside the absolute value bars, what number could you put there that's not going to change the outcome? 1, because it's multiplication. All right? Then why are H and K 0 if I don't see them in the equation? They're not 1. We just said put a 1 because the A is not there. And now H and K, it's zeros when they're not there. Good. So when it's subtraction and addition, it's a little bit different, right? If I want to multiply and I want to pick a number that if I don't write down, it's okay because it doesn't change the multiplication outcome, that number is 1. But if I want to pick a number that I don't write down if I'm adding or subtracting stuff, if I add 1, does it change the outcome to something? Yes. So now the number that wouldn't change it if they didn't write it in addition or subtraction would be 0, and that's why those are determined to be 0. Okay? The vertex is which point of the graph? What do you think they're talking about when they say vertex? Good. So it was kind of the boundary of our piecewise functions where we switched from graphing one function to the other, but it's both the x and y coordinate. So you guys have dealt with vertex points before when you graphed parabolas. They had a vertex point as well, right? It's like the place that the graph turns around, right? And then opening up or down is just which way the V is facing. Okay? So if you don't have a calculator, go ahead and get one. We're going to talk about how to type this into the calculator so that you can quickly see it. When you go to your y equals, clear out anything that's already existing there. We want to focus on our equation for today. If I'm going to do number 2, I go to my y equals. I want to type in 3 times the absolute value of x. We already know where 3 and x are, so here's 3. The only question is, where is the absolute value function? So on your calculator, right below the green button, there's a button that says math. Kind of funny that that's on the calculator, right? What does it really do? It just has some different mathematical functions in there. So if you press that button, it's going to bring up lots of menus. If you scroll to the left and to the right, there's different menus up top. We want to go to the num menu. Those are functions that take place that you can apply to numbers. Okay? Notice it has things like rounds it, take it to different integers, minimums or maximums. But the very first one says ABS. Okay? Yours might look slightly different if you have newer software, but it should basically do the same thing. When I press enter, it's literally going to print this like computer language on my calculator. Those of you that have the newer software or are using one of my yellow calculators, when you press enter, it's going to make nice little absolute value bars for you with a cursor in between. Okay? So I'm going to go ahead and choose that by pressing 1 or enter. It's going to type that right where I was. Oh, I have the newer software. See, I got absolute value bars. See how that looks? Okay. If you didn't get absolute value bars, but you got A, B, S, and an open set of parentheses, that's correct. Just type inside of the parentheses the same thing I type inside the absolute value bars. So I want X inside the absolute value bars. So I go ahead and press X, and then I can just arrow outside the absolute value bars and be done with my absolute value. Those of you that have the parentheses, you want to type X, and then you want to type a closed parenthesis just to let the calculator know that you're done with what's inside the absolute value bars. Okay? Then make sure your window is on that standard window we had before. So if you don't know, just go ahead and press zoom and choose choice 6. And then you see the graph. Okay? So what you're going to do on the handout is you're going to quickly sketch the graph. You're going to say what A, H, and K are for this equation. You're going to say the vertex point and whether it opens up or down. And while you're doing this, I really want you to think about how are these different numbers affecting the graph. Can anybody see what we did by multiplying the equation by 3? How was our sketch affected? What is the difference between what we see here and what was originally sketched for the first parent function? Good. Okay, so this V got narrower, right? Because these lines don't have a slope of 1 anymore. What is their slope probably going to be? 3, because we put that 3 in, okay? Does everybody understand what you're doing right now? Okay, so you have 7 equations to do this for. You can split the work up in your group. If there's people that don't have access to calculators, they can do all the A's, H's, and K's. Someone else can do all the sketches. Someone else can do all the vertex points. I don't care except for that I need you to be done, let's see, 54. We're going to try to do it in like 8 minutes, okay? So split them up. One person do one person do another, and then share the information. Do you guys understand? Okay, so that means you shouldn't have to do more than 2, okay? Oh, because you have on. So see this thing up here that's highlighted? That's for like plotting data. So I'm just going to, I'm going to go up to it and press enter. Now it's not highlighted anymore. And then you shouldn't see this. Okay, let's talk about this a little bit. Okay, we talked about number 1. We're going to kind of randomly select some here. In number 3, can somebody raise your hand and tell me the A, H, and K value that you got? Yes. Good. Okay. And then what was different about your sketch in number 3 than the parent in number 1? Yes. Good. It was facing downward. So what do you guys think makes it face downward? Yeah. The negative. What about the numerical part of the A? What is the 3 doing? What is the 2 doing? How did those graphs end up different from your parent besides the facing down part? Lauren? Good. It's affecting the width of the V that you're seeing, okay, because it has to do with the slopes of the lines. Where were the vertices for these 2 graphs still, number 2 and number 3? Still at the 0, 0 vertex that it was before, right at that origin of the graph? All right, let's look at number 4 and number 5. What, the A, the H, or the K, what is changing from the parent function in graphs number 4 and 5? The K, only the K, right? They both have the same A value as the parent function and the same H value, but the K was changing. It should be 1 here and -4 here. Then how is the K affecting your graph? What are you seeing in the sketches that's different in numbers 4 and 5 than your parent function in number 1? The y-intercept, okay? So it's literally moving the V up or down, right? And so how did that affect the vertex point? What coordinate of the vertex point changed? Okay. Good, the y-coordinate of the vertex point changed, right? So then you get to 6 and 7. What's different about 6 and 7 compared to number 1 when you look at the A's, the H's, and the K's? Yes. The H's change, right? So we should still have 1 as our A's and 0 as our K's because there's nothing being added or subtracted outside the absolute value. And here's where things get a little tricky. What did you guys get as the h value for number 6? Yep. Good. Okay. -3. Why -3? It says +3. I'm very confused right now. Enlighten me. Yes. Good. Remember that the formula was written as x minus h, meaning the number you put in comes after a minus sign. If I put a +3 after the minus sign, will the equation look like x plus 3? No, it'll look like x minus 3 when a +3 is in for h. So if it looks like x plus 3, what they really must have put in for h was a -3, and the minus the negative is what made it look like a plus in the final version of the equation. Okay, a little tricky with the h's, right? So here the h was actually -3, and then what was the h in number 7? +2. Okay. And what did changing the h change about your sketch of your graph compared to the parent functions? Or? Say that again, sorry. Good. It was a horizontal shift, right? It moved your graph either to the left or to the right and changed what part of the vertex? The x-coordinate, because it's moving it to the left or to the right. Okay? All right, so here is what we need to know to be able to graph these. And you guys talked about this. How can we tell whether the equation opens upward or downward? It's going to open upward if a is positive, downward if a is negative. Okay? We won't have an a, or we won't have a v if a is actually equal to 0, because if you're multiplying your absolute value by 0, everything is just going to become 0. Okay? So that's why 0 is not included in these little analysis here. So what else does a affect about the graph? Lauren already answered it for us. She said it affects the width of the v. Okay? And we'll see exactly how that happens. What did we say changing the h does to the graph? What did it do? Good. Okay, so this is a horizontal shift. It basically really affects the x-coordinate in your vertex, right? It's shifting the whole graph either to the left or to the right. Okay? Slightly different from that, then what would we call the change that k is causing the graph? See, Lauren, she's all over it. Come on, people. Can't let a couple people carry you. If h is a horizontal shift because it's changing the x-coordinate, yes, ma'am. Good. Then k must be a vertical shift because its focus was on moving the v up or down and was really focused on changing that y-coordinate. Okay. So knowing these things about absolute value equations and graphs basically allows us to take an equation, kind of dissect it and look at those parts, and quickly be able to draw the graph of any absolute value function or write the equation of any absolute value function. Okay? Just tell me when you're good. I see a couple people writing still, so I'm going to wait a second. So if you didn't have the note guide, you should write the general form of the equation, and then you should make some notes about what a is determining, what h is determining, and what k is determining, so you have that information. Okay? All right. Okay, so if we had to write the equation for this function, and sorry, it's a little hard to see where the x and y axis are, so I'll outline those for you. Okay. We know its absolute value because of its shape. So h is the horizontal shift. The parent function had a vertex here at the origin. This graph has a vertex right here. What was the horizontal shift that occurred? How did it move? 2 to the right. Okay, meaning h is a +2. So when I plug in +2 for h, remember in the equation it looks like x minus 2. what was the vertical shift that occurred for the vertex? So instead of being on the x-axis, it's one above. Okay? So k is a positive 1. And it got wider because rather than the slopes of the lines being up 1 over 1 and be like that, the slope appears to be up 1 and over 1, 2, 3, 4. Okay? Which means my A value is going to be rise of 1 for a run of 4, or 1/4. And should the 1/4 be negative or positive? Positive because the V is opening upward, and I know that I would only make it negative if it opened downward. Okay? Yes? Yes. A is like the slopes of the lines. Okay? We're going to use a little bit different terminology later, but for now, that's fine. All right, so when you're given the equation and you want to create the graph, the same information that we just needed to build the equation is what you want to pull out. So we're almost faster graphing these by hand once we see all these patterns than it takes to actually type it all into the calculator correctly, right? Because it's only a few steps, okay? So what would we start with? Let's see, let's pull out the important stuff. A, H, and K. What is our A value? Look at the equation. What's our A value? Somebody new that hasn't talked to me yet today. Yes, sir. Good. Okay, what is our H value? Yes. Good. What is our K value? -1. How do I determine where that vertex point is? So for the parent function, it was at 0, 0. Where is it going to be now with these shifts? Yes. Good. H affects the x-coordinate, K affects the y-coordinate. So my vertex will be at -3, -1. Okay, sorry, my graph is like scaled really small. Okay, you can just sketch your own on there. Now, do I expect the V to face downward or upward? Downward, because the A is negative. And then I can use a slope of 1/2. So I'm going to go down 1 over 2. That creates one side of my V. And then remember, you need to reflect that to have the other half of your V. So down the other way. Both of these lines don't have a slope of -1/2, right? One of them technically has a slope of +1/2. But we know the shape of the absolute value graph. We know negative A means downward V. So we just draw it appropriately. Okay? All right, the last thing I want to look at before you guys leave is what if it's not set up the way that you would want it set up, okay? So what's wrong with what's up here, so to speak? Yes? Yeah, the A is inside the absolute value. Sometimes with some functions, it's very easy to get the A value outside of the function. Other times it's very difficult. We're going to learn how to deal with it when it's inside without taking it out, but not for absolute value functions. We treat them a little simpler because they can all easily be written in another form, and here's why. The absolute value of 3 times 5 is the same thing as the absolute value of 3 times the absolute value of 5. That's not true for everything. That's true for absolute value, so I can use that idea here. So basically what I would want to do, since I don't like that 2 there, is I would want to rewrite what's inside the absolute value function by factoring out, it's still within the absolute value, but I factored out the 2 because I don't want any number in front of x inside there, right? That didn't fit our format, okay? The reason this helps me is because this is a 2 being multiplied by an x minus 2. We said that 3 times 5 inside of absolute value is the same as if 3 had its own absolute value around him and so did 5, which means we can split this up to 2 different absolute values multiplying each other. And the reason that helps is because you can calculate the one that just has a number in it. What is the absolute value of 2? 2. And now could you go ahead and finding your A, H, and K, would you be able to graph that equation? Yeah, very quickly by hand, right? Okay. But you can't always just take the number and put it in front. If that had been a negative 2, just a little side note real quick, if it had said this, oops, yeah, this is negative 2 times x plus 2 now. And then when we split this up, it looks like this, and this would become 2. See how that equation would change a little bit more than ours did? So you do have to think about it. You can't be totally on autopilot. But our absolute value equation's pretty nice to graph. Yeah, if you can memorize the format of the equation and know what each piece does well, it won't be too bad. Yes, sir?